Welcome to part 4 of the series on number theory and computations. And in this one, we'll be looking at converting between different bases. So the first step we'll look at when converting between bases is conversions to base 10, something that we're all too familiar with from the last video. And if you haven't seen it, I'll link it somewhere on screen. So for example, let's convert 3,203 in base 4 to base 10. We drop our place values 4 to the 0 power, 4 to the first power, 4 to the second power, and 4 to the third power, and we place our respective digits. We get 3 multiplied by 4 to the third power, plus 2 multiplied by 4 to the second power, plus 0 multiplied by 4 to the first power, plus 3 multiplied by 4 to the 0 power, which simplifies to 3 multiplied by 64, plus 2 multiplied by 16, plus 0 multiplied by 4, plus 3 multiplied by 1. So the sum of 192, 32, 0, and 3 equals 227, which is our original number in base 10. Second example, 7,234 base 8. Again, we write our place values and then place our respective digits. We get 7 multiplied by 8 to the third power, plus 2 multiplied by 8 to the second power, plus 3 multiplied by 8 to the first power, plus 4 multiplied by 8 to the 0 power, which simplifies to 7 multiplied by 512, plus 2 multiplied by 64, plus 3 multiplied by 8, plus 4 multiplied by 1, and we're left with the sum of 3,584, 128, 24, and 4, which is 3,740. So we know how to convert from any number to base 10. Next, we learn how to convert from base 10 to another base. So for example, 32 to base 2. We draw up a division table. That's the first thing we do. And then we say 32 divided by 2. That goes 16 times exactly, with remainder 0, and we write down this remainder 0 some part aside. Next, we have 16, and we divide it by 2 to get 8 exactly. Again, that is a remainder of 0. Next is 8 divided by 2, which is 4, and that leaves a remainder of 0 as well. Now we have 4 divided by 2, which is 2, and gives a remainder of 0. 2 divided by 2 is 1 exactly, and the remainder is 0. Next, 1 divided by 2 is 0, since we cannot get a 2 from 1. However, the remainder this time is 1. And we now read the remainder numbers from bottom to top, which in this case is 1, 0, 0, 0, 0, 0, and this is in base 2. So 32 written in base 2 is 100,000 base 2. Another example. Next, what is 35 written in base 4? So 35 divided by 4 is 8, but we have a remainder of 3, as 8 times 4 is 32, and 32 from 5 leaves 3, so our remainder is 3. Next, 8 divided by 4 is 2 exactly, with remainder 0. Next, 2 divided by 4 is 0, and we have 2 left as a remainder. And we now read the numbers from bottom to top, so we have 203 in base 4. Or third example, 3,744 written in base 7. Okay, so we divide 3,744 by 7, and that goes 534 times with a remainder of 6. Next, 534 divided by 7, well, that's 76 with a remainder of 2. 76 divided by 7 is 10, and that leaves a remainder of 6. 10 divided by 7 is 1, and that leaves a remainder of 3. 1 divided by 7 is 0, and we have 1 left as a remainder, which means we're done. And reading from the bottom up, we get 3,744 is 13,626 in base 7. Okay, so if we scroll back up, we see that when we write a number in base 2, for example, since we're dividing by a 2 throughout, then the remainder can never be 2 or greater, right? The remainder is either a 0 or a 1 because we're dividing by 2. Likewise, for base 4, we're dividing by 4, so the remainder is either 0, 1, 2, or 3. And when we write numbers in base 7, we're dividing by a 7, so we can never get a remainder that is 7 or greater. The remainders are either 0, 1, 2, 3, 4, 5, or 6. And this brings me to my point. If we're working in a particular base, then the digits in the number are 1 less than the base we're working in. So if we're working in base 2, the digits are 1 and 0. If we're working in base 3, the digits are 0, 1, and 2. If we're working in base 4, the digits are 0, 1, 2, and 3. If we're working in base 8, let's say, the digits are 0, 1, 2, 3, 4, 5, 6, and 7. And if we're working in base 9, the digits are 0, 1, 2, 3, 4, 5, 6, 7, and 8. And this brings us to the last thing for this video. If we're converting from one base to another, then we first have to convert to base 10 as an intermediary step. So this kind of brings in everything that we've been doing so far. So for example, 3,203 base 4 to base 2. The first step is to convert 3,203 base 4 to base 10. And at this point, this should be elementary stuff. We write the place values, 4 to the 0 power, 4 to the first power, 4 to the second power, and 4 to the third power, and place our respective digits. So we get 3 multiplied by 4 to the third power, plus 2 multiplied by 4 to the second power, plus 0 multiplied by 4 to the first power, plus 3 multiplied by 4 to the 0 power, which is 3 multiplied by 64, plus 2 multiplied by 16, plus 0 multiplied by 4, plus 3 multiplied by 1. And this leaves us with the sum of 192, 32, 0, and 3, which is 227 in base 10, of course. Next is to convert 227 to base 2. So 227 divided by 2 is 113, and that leaves a remainder of 1. Then 113 divided by 2 is 56, and that leaves a remainder of 1. 56 divided by 2 is 28, the remainder is 0. 28 divided by 2 is 14, the remainder is 0. 14 divided by 2 is 7, and the remainder is 0. 7 divided by 2 is 3, and the remainder is 1. 3 divided by 2 is 1, and the remainder is 1. 1 divided by 2 is 0, and the remainder is 1. And now, reading from the bottom up, the answer is 111,000,11 base 2. And so 3,203 base 4, written as a binary number, is 11,100,011 in base 2. And this is the end of this video. Like and subscribe so you'll be notified whenever we post a new video, and share with others who might be interested in this content.